we now move on to a different component. Yesterday there were some group asking questions about welding. I think we can talk about welding. Let me see which, I forget which chapter, so we will find it. Let's well, yes. Okay, so welding is like this, and the cross section usually looks like a triangle if it's at the perpendicular corner. Okay? So if you view it from the side, that's how it looks like on the left in the left figure. If you take a look from the like the front, then it looks like something like the right figure. Okay, so there are symbols to represent what kind of welding it is. I'm not going to go through this. I think you probably have learned about this when you learn graphics, engineering graphics. If you have not, that's okay. In the future, if you see some kind of arrow pointing at some corner, that's a symbol of welding, and it's describing what kind of welding. You can always Google for this information. So I'm not going to cover this. Not the main point for this chapter. Yeah, there are symbols like this, basically describing its shape, and yeah, something like that. So, and engineering drawing could be something like this, indicating the shape of the welding and some dimension. Okay, so basically, there are one for face to face. Sometimes, if you have a groove, it allows more welding material in the middle. Because if you have face to face with very narrow gap in between, you may not have enough welding material at the middle, so the bonding may not be good enough. Okay? So what about the design for welding? So the main point of design of welding is to study the load or the stress inside the welding material and determine whether it's gonna fit. Only focusing on the welding material. Okay, so this chapter is about estimating how much stress that is inside the welding material. Okay, so if you take a look at this particular figure, you can see that following the most fundamental equation, stress is basically force over area. So over here, this is like the face-to-face welding. Then usually for welding material, there's a term called throat. It's like a most narrow part inside the welding material if you view it from the cross section. So that distance is like neck, is like the width of the neck, okay, the throat. Sorry. So over here we use the width of the throat or like the neck as the characteristic dimension or the most important dimension for stress area. Why do we focus on the most narrow part? If you focus on this particular length, this length is a lot longer. And if you compute for the stress area, you use this tilting length multiplying the total length of the weld, then you have some particular area. And if you, on the other side, if you use the throat to compute for the area with the throat will be the smallest. Smaller area means greater stress because stress equals to force over area. So we only care about the worst loading condition. So that's why we only focus on the narrowest area inside the welding material. Okay, so for this face to face, the stress area is H times L. And similarly, if you apply the force in the shearing fashion, then it's still the force that caused the shearing force, the shearing stress, over the stress area, that's your shearing stress. And how about the triangular shape in the cross section? So basically, just like what I said, you need to use the throat to measure the area. So use this throat multiplying the total length. That will be the stress area of this weld. Okay? So that would be the key. If you do not know about this, sometimes when you do welding, maybe they ask you to weld this corner with certain dimension. Maybe it will tell you, okay, 5 here, 5 here. So when you study for stress, you may just use, okay, 5 times L, that's my stress area. But in fact, if you analyze the weld material right here, this length is the shortest and area smallest. So the stress is the largest. Okay? That's why we need to study the most critical stress area. Okay? So that's the key for welding design. Now, these are just different examples of load balancing. So from here you can see if you have a very unique weld material in a particular shape with two triangles, then you may have more complex forces with some of the normal force and some of the shearing force. So then you need to do load balance. Okay? Anyway, let me move on to the most common problems. Right here. So that's why you have this 0.707. That's basically by the cosine 45 degree, you will have the 707 right there. Now, for this particular problem, you can see that because you now here have this triangular shape, so the shearing force is not only F over HL, it's actually with this pre-multiplier at the bottom due to the throat dimension. Okay. Now, this is the most typical problem you can see. And if you have never learned about this before, you probably will know this is how actually the mechanics that's happening inside the weld material. So what does this drawing mean? Imagine you have a metal plate and you are going to stick with another metal plate. Without bolt, what do? You weld. Okay, if you want to weld, what can you do? You will be welding right here, right here, right? So the welding material are like the glue for fixing both metal materials. Now, if the top part is being welded, if I draw some small crosses to represent the position of the weld, okay, so these areas are being welded. Now, if I apply a force right here, what's happening? It's providing some kind of torque. So that particular torque is going to be carried by what? By the forces and the stress inside the weld material. So it's actually these two stripes, those two strips of weld material that are carrying, having a reaction to counterbalance the moment generated by the external force. So that's what this figure is about. But the material right here is it has an area. So do you have the same force and stress everywhere? Actually not. So what's happening is you need to figure out at which point it is carrying the most stress. So if you figure out, okay, there's one particular point that is carrying the largest stress, that means when the weld material fail, it starts with that particular point. So for this kind of problem, we need to figure out what is the worst loading position, and we want to make sure that position is safe after you apply certain load, then your design is fine. Okay, so that's what this figure is about. Now, when you apply this force from top to down, you actually have a pulling force down. Okay, so this tau means due to this force, there is a kind of shearing stress coming down. It's like pulling the whole plate downward. So this is the first part of the shearing stress. And the second part will be this tau double prime, which means there is actually a rotational center right here. And when you have this moment, the whole thing is going to rotate about this center. And about this center, perpendicular to this radial direction, there is going to be a tangential vector going clockwise. That is the shearing stress due to this rotation. Okay, so that particular point has two parts of the shearing stress. One is along the along the loading direction. The other one is along the rotational direction. So right here, the first part equals to the shearing force over the stress area. The second part, that would be you will be using basically the balance of moment to compute for the shearing stress. So with the combination of both, the total shearing stress at this particular point is actually here, a combination of two vectors. So the main point is that you need to figure out this total shear everywhere. So if I make a drawing of some critical points, like this one, and this one, okay? So all these 4 points will be experiencing the same uh, 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 shearing stress downward. So it will have the same amount of shearing stress. So they are all tau prime. Okay? And how about the torque, the shearing stress due to rotation? So you then need to draw a line along this radial direction. You kind of make this 90-degree tangential line, okay? And then you know one would be going this way, this one would be going this way, and that one going up. So in this particular case, the combination of this corner point at the left lower corner ends up with a shorter vector for the total shear because the spanning angle between both shearing stresses are greater than 90 degrees. So the combination of both is not a long one. Okay, so this one is fine because the total shearing stress is not as large as that one. Similarly, the total shear is, this one is like that, and this one would be like this. So it would be a long vector as well. So the critical point would be either this one, or they may be the same amplitude. If they are having the same amplitude, then that means when it fails, both two positions may be the worst position to fail first. Okay? So that's the idea. Now we are going to, if you understand this idea, then we can now do some problem formulation like this. The issue is how do you find the rotational center, right? So this is an example to show you how to get the rotational center. So this is a unique example where you have a vertical weld and a horizontal weld with different sizes. So the problem specifically designed in such a way so that you can also compute for the rotational center even when the sizes for the weld are not the same. So right here, whenever you make a drawing with the width T1 and T2, it actually already consider the dimension of the throat. Okay, so this is like this pink area represent the throat area inside the weld material. Okay, now first you compute for the total area. So this is a total A. Okay, so basically that's easy, and you will need, because you are doing shearing in polar coordinates. So you actually you will be using the polar moment polar area moment. Okay, what is it called? The polar moment of polar moment of inertia. Okay, so basically, in the past we usually compute for I x x and I y. Now you compute for IZZ. So IZZ actually is J. So how is IZZ being computed? Basically, Ixx plus Iyy. Okay, so right here, this is the equation, and Ixx, Iyy, you can use the basically what we usually know is the b h cubed over 12 and the b cubed h over 12. These are the two equations for Ixx and Iyy, so that's why you will see these two equations right there, and that's how you compute for j. And for here, it computes for jg1. So it's the j of the first area at the G1 point. So it's JG1. And it also computes for the J at this point, JG2. So that's the polar moment of inertia about the center of G1 and G2. It's not the polar moment of inertia about the rotational center. So we then need to compute for the total polar moment of inertia about G. So how do we do that? Using this equation. It's the parallel axis theorem. Okay, parallel axis theorem. So for moment of inertia, if you have an area and if you compute for moment of inertia about its center, so that's the original, you can say it's like IO, about its own center. But if you have a different center, let's say G point, so what would be IG? So IG would equals to the moment of inertia about its own geometrical center plus the area of this geometry of this shape times the square of its radius. So that's the parallel axis theorem. Okay, that's how you can compute for the polar moment of inertia about some center outside of its own geometrical center. So you need to do that for this JG1. You need to shift its rotational center to here, and you need to do the same thing for this part as well. So you shift both to the G and then sum them up. So that's why you have a plus right there. Okay? So right here, this part is about computing for the center of it's like the geometrical center of everything. Okay? So how is it being computed? Basically, you can think of every material has a density, and this G point is like a central support point. You need to put your finger somewhere, so the weight of each density will balance out when you point this finger right here. And that's how you can compute for this X bar. Similarly, you can think of the gravity direction is going toward right, and then you have a finger right here. You are trying to find, okay, where is the position of G? Okay, right here, so that the density of the lower part is going this way, having a moment counterclockwise, and the other part of the density above G has a moment clockwise, and these two will balance out due to a support right here. So you need to find out where is that position, Y bar. So just imagine this area has density and use balance of moment to find it. So these are actually calculation of balance, moment balance. Okay? So how do you do that? right here it's like a x bar equals to a1x1 plus a2x2. But what does it mean? For this equation, basically, it's like you are having a support center right here at 0, and you have a total. This is like a reaction force. You are supporting the whole weight. So the whole weight is the whole area. So that would be A. The A is like you have a supporting force, okay, like an A, and then times the total length, A bar. So this is like a supporting force carrying the entire weight, and carrying, so that this part is generating a counterclockwise moment like this. And the other side, the other part would be this smaller part, and the A1 part, that is generating some weight coming down, and area is on weight. So this A1 times X1 going clockwise. So A1 X1. Similarly, there is an A2 going this way. So A2 times X2 clockwise. So the balance of the counterclockwise moment with the clockwise moment, and then you just plug in all the numbers. Then you can compute for x bar. Similarly, do the same thing on the y direction. Okay, and once you have that, you need to compute for R1 and R2 because you need that in the parallel axis theorem. So R1, R2 will be just a geometry. Okay? So, do you understand this one? Like for the group, if you are studying for welding parts, then you need to figure out something like this. Because once you have those information, they are necessary for the stress analysis. So you need to first get J, rotational center G, positional G, and the total J. Without those, you cannot compute for stress. Okay? So this is for the first half of stress analysis. So the second half, basically, once you have the J's, you can then apply for the stress, like this particular problem. Okay, you can see the weld geometry looks like this, and it's compute for the total area, and there are certain force applied. So force over area, that's the stress along the force direction. Okay, and the interesting part of the rotation is you need to find out where is your rotational center. So from here, you need to know the rotational center is right here. So you use the centric to figure out where that point is. Once you have it, once you have the center, then it's basically computing for the shear stress that is following this rotational direction, the tangential direction. So you have the J, the total J, you have your moment, and you have the radius. You can compute for this rotational, the shear stress in the tangent direction. So how come the tau AB and tau CD are different? Okay, right here, it's trying to analyzing the shear stress about this rotational direction. They're treating A, B, and CD separately. How come? It's symmetrical from left and right. So the radius right here are the same, and the shear, the tau double prime for C point will be going this way, and then for the shear going, it will be clockwise. So the tau double prime will be going that way, and they have the same magnitude because they have the same radius. But for B, it has a wider radius. Okay, so the tau double prime will be different. Okay, it's different because tau equals to n radius over j. So right here, the radius is different, and over here it has a larger radius. So the stress, this arrow is longer than this one. Okay, similarly, you can draw a radius right here, draw an arc. So the stress will be going this way. Okay, they are having the same magnitude, and they are larger than the stress in CD. So right here, the stress at AB are larger, stress at CD are smaller. But does that mean the total stress will be the largest at A and B? You don't know. You need to then figure out the combination of stress. Like this, yes. So over here, how come it's drawing the whole thing in an opposite direction? So it really depends on whether you are trying to study the direction that is due to external force, or you are studying the stress due to reaction force. They are basically they are the same magnitude, but it's like either positive direction or negative direction. Either way. So for this particular drawing, it's representing the stress along the reaction forces. Okay? So this is an external force going like clockwise. So all the stress due to reaction forces are going counterclockwise to balance out the one that was applied externally. Okay? So over here because of the force going left to right, so there will be a shearing stress going right to left everywhere. That would be the horizontal ones. And due to the external force right here and the rotational center right here, there is a moment going clockwise. So all the reaction forces everywhere is generating shearing stresses, having counterclockwise balance. So going this way. And then, so at 4 different points, their stress conditions become very different. And then from here, you can see C and D points probably would have a longer vector of the total shear stress. Probably. You need to recompute it. So, most highly stressed points, C and D. So before the analysis, when you see some weld like this, like it's like you have a structure. Okay, let me weld. How do you weld? You don't. So it's like you are welding. Sorry, let me occupy one moment. You are welding like this. Okay, and it's like there's a handle, and you are pulling the handle, allowing, trying to rotate the plate in this way. So without calculation, you don't know whether this point is gonna break, or this point is gonna break, or this one, or this one. So after the analysis, you now realize, these two are the critical points. So are they always the critical points? You don't know. You really need to compute it, because the amount of the total stress is very close. right here, at AB, the total is 37, at CD, total is 42. Maybe when the geometry change a little bit, or the load change a little bit, it could be, the worst condition could be at the bottom. We don't know. Okay, so that's why you cannot just look at the shape of the well and then make a guess. These two are the most critical. You have to truly compute for it. Okay, so that would be on everything I want to cover for welding. Okay, but for the rest of the book, it's just exercise for different shapes, but similar idea, like basically analysis in different shapes. So once you have the stress, basically you just want to make sure the stress is smaller than yielding stress, and you can apply the safety factor. All the design equation can be applied here. So the key of this chapter is to compute for the stress. But the way to compute for the stress is very unique in this particular chapter. That's why you need to know. Then you know. Okay? So that's it for today. Next week I will then talk about screw and bolt. Because some group are also analyzing screw and bolt. Okay? Thank you.